Okay. So that brings up a different type of question that I could ask. I've always given you the polynomial. I've said, hey, list all the zeros, factor completely. What if I give you a list of zeros and say, find a polynomial that has these zeros? Find a polynomial that has zeros, -1, -1, and 3i. Okay, it's a little different, but cool. Well, what we'd say is if -1 is a 0, x plus 1 is a factor. And if -1 is a 0 again, x plus 1 is a factor again. And if 3i is a 0, x minus 3i is a factor. And because this is complex, this has to occur in a conjugate pair. So that means that x plus 3i must also be in there somewhere. So here we have a function that has -1, -1, and 3i as zeros. And then from there on, we would simplify and multiply this thing up. Okay, we are going to expand our meaning of completely factored, and we are going to do that by, whoops, I meant to draw a line. We are going to take a function like x to the 4th minus x squared minus 20. Okay, what we're going to do is we're going to factor this. We are going to factor so that it's irreducible over the rationals, irreducible over the reals, and then finally, completely factored. Okay, so when we see this, it's x to the 4th. We're really not, generally very good at factoring such things. And given our recent history, we might be tempted to pick out our possibilities, factors of 20, and start doing synthetic division until we can find a couple, and that's fine. But I like to pull in examples that show tricks here and there, and this is a good one. You might notice we have x to the 4th minus x squared minus 20. It appears to be quadratic, and it is. We can actually factor this thing. If we break x to the 4th into x squared times x squared, now we need factors of 20 that have a difference of 1, and that would be 5 and 4. Okay. And each time you factor, you look inside your parentheses and you see if it can go again. X squared minus 5, we have a binomial, a difference. It is not the difference of two squares because 5, of course, is not a perfect square. So, in Algebra 1 and Algebra 2, we would leave that alone. Over here we have x squared plus 4. Well, that's a plus, not a minus, so it is also not a difference of two squares. And in Algebra 1 and Algebra 2, we would leave that alone. And this is irreducible over the rationals. Now, if we look at the reals, 5 is not a perfect square, but we can certainly take the square root of, right? So this could factor. We could pretend it was a perfect square, and we could say that it factors into x plus the square root of 5, x minus the square root of 5. And now it is irreducible over the reals, right? Square root of 5, irrational, but still real. Now, completely, that means, all the way, everything is completely factored out. It is as far as you could possibly go. And we've done that here, but with this x squared plus 4, we could not factor that over the reals because we'd have to look at this as x squared minus a -4, and you can't take the square root of a negative number when you're only limited to using real numbers. you have to go into the complex number system. So for C, to factor this completely, leave this part alone. And we saw this one before. Remember before we looked at this. I'm going off to the side here. We looked at that as x squared, and instead of that plus, we replaced that with a minus minus, which is perfectly legal. So now we're going to look at this difference of two squares. So I have x plus the square root of negative 4 and x minus the square root of negative 4. You can't leave it like that. That is just too ugly. So I'm going to call this x plus 2i, x minus 2i. And now it is completely factored. Rewind that one if you want to hear that one again. This is a very good test question to factor it over rationals, reals, and then completely factor it. So it might be worth checking out again. So let's put all this together and let's bring it home. And let's take a new function. Let's go with a fourth degree. Okay. Let's list all zeros, factor completely, and that's 60. That is going to take us a long time, right? Way long. So let's go with a hint. Given that 1 plus 3i is a 0. Oh, well, so we already know one of the zeros. Actually, we know two of the zeros. Why? Complex roots come in conjugate pairs. So if 1 plus 3i is a 0, then 1 minus 3i is also a 0. So we've got two. So there are a couple ways that we can go here, and I'm going to do them both, and you can pick which one you like. They're good to see at least once. Let's see. So the first time, let's do it this way. I know these two items right here are zeros. Okay. That means that x minus 1 plus 3i is a factor, and I know that x minus 1 minus 3i is a factor, right? Because if I knew 5 was a 0, x minus 5 is a factor, right? If I knew fire truck was a 0, x minus fire truck is a factor. If I knew 1 plus 3i is a 0, x minus 1 plus 3i is a factor. Okay? Alright. So what I'm going to do, I'm going to multiply these two factors together, and I'm going to divide that into the function and deal with what's left. Because I know these two are zeros, so if I multiply those together, it's going to give me a trinomial. Since we have conjugate pairs, remember when you multiply those together, it makes the i's go away. So I'm going to end up with a trinomial that I can divide into this function, and it's going to leave me with a quadratic, because when I multiply these two together, x times x is x squared. I'm going to divide x squared into x to the fourth and end up with a quadratic, which I can hopefully factor. If not, quadratic